In this video, we'll go over the different types or different techniques, there are more types, of proofs and proofreading. We will, in this section of the course, focus mainly on direct proofs, proofs by contrapositive, and proofs by counterexample. The other types of proofs that I'm going to go through and show you guys, we'll see a little bit later on in the semester. Okay, so the first guy is the direct proof method. And what you do in terms of this direct proof method is you link together the rules of inference and you just chain them all up, sort of like a little daisy chain thing, and you get to some conclusion. Okay? The direct proof method, if you're proving something is true, is the most straightforward way of proving something. It literally is just linking all of the logical steps together. Okay? Now, there is a second type of proving method, or second type of proof, called an indirect method. Your book calls it an indirect method. Almost everybody else in the world calls it a proof by contrapositive. Now remember what a contrapositive statement was. If you started off with an if-then statement, so direct proof says you start with your if-then statement, you start with the if part, you get to your then part using rules of inference. Proof by contrapositive, or the indirect method, first step you do is you're going to look at your contrapositive. Now remember what the contrapositive statement was. The contrapositive statement said you negated both the if and the then part and you flipped the direction of the implication. Once you've gone ahead and looked at your contrapositive, you're then going to just do a direct proof on the contrapositive statement. So this proof by contrapositive literally just has one extra step where you convert your original statement that you're asked to prove. The next type of proof is a proof by contradiction. Depending on time, we may not even go over proof by contradictions, but basically the idea behind these guys is you make some assumption. So make some assumption. And then what happens is you go forward under that assumption. Specifically, you typically use a direct method or using a contrapositive. Either way is just fine. And you made that assumption, then somewhere later on in the proof, you find something that just isn't true. So maybe it's something like 2 and 3 are the same number. Maybe it's something like you get a fraction that's divided by 0. Okay? Something that in your world is legitimately not true. Then you say, oh, well, that assumption that I made earlier, that assumption has to not be correct. So you go back, you fix it, and then that gives you some result that you wanted. Okay? Proof by contradiction is probably the hardest of all of the types of proofs that we'll see. We'll also have a dealing with a counterexample. Fair warning, counterexamples do not prove something is true. Counterexamples show where something is false. Because remember, inside of a proof, if we link this back to truth tables, we are looking at our compound statement that we would have built if we did truth tables, has to be a tautology. The counterexample finds the row, essentially, that doesn't equal a truth value of true, it equals a truth value of false. So this here is where we find an example where the statement is false, and this allows us to stop almost immediately and then say, oh, well, this statement isn't true, we're done. Okay? Fair warning, if you want to show that something is true, examples are awesome in Scratchwork to sort of get an idea to yourself of how things work, but examples in a proof will never get you to the right answer unless you have a counterexample. In other words, where the statement failed. Okay? And the last type of proof that we're going to be looking at is something called mathematical induction. And mathematical induction we'll get to later on in the course. Okay? So now the types of proofs that we're going to be looking at are those 3 different types of proofs. So let's go and look a little bit more in detail at direct proofs, because they're the ones we're going to be looking at the most in this section, and then we'll look at some examples of all of these guys. So here's the structure for a direct proof. First thing is you're given some mathematical statement. Any mathematical statement can always be written in the format of an if-then statement, even if the if part is I'm alive. Okay? So you have the if part of the statement is what you start with. It's your givens. It's your starting point. Your then part is whatever the conclusion is, whatever the result is of this mathematical fact. Okay? Now, in terms of the actual method, the first thing that you would do when you're writing the proof itself. So this is the thing that we're doing instead of writing truth tables, instead of doing all of the symbolic logic that we've just gotten out of. Here, the very first step is you're going to state what you know. Please note, all of this stuff right here is going to be in sentences. Think of this as like a little 5-sentence paragraph that you are building. Okay. Except it's on a mathematical topic and you're trying to convince somebody that what you're saying is correct. Okay. Second thing that you would do after you state what you know, please note stating what you know is exactly the same thing as stating that P statement from the logical implication. Make sure you actually put it together in proper English sentences, but that's the information from your P statement. Second part is you use any definitions, theorems, facts, etc. to rewrite the information that you need in a more conducive format to work with. Typically definitions, and remember theorems are those buzzwords typically for some sort of formula, okay? But definitions are big here. Third sentence that you've got, or third component that you've got, is where you start using your logic. This is where you pull out your rules of inference. This is where you pull out algebra. There's in the level of math that we're going to be in. Typically what you'll see in the middle part of the proofs on this step 3 right here is where you actually have some a little bit of algebra formulas going on, where you actually do what before this class you might have thought of as all that you'd need to do. In other words, do the math part. Okay. Then we're going to, and actually here, let me rewrite this. Then we have where you use any definitions or theorems to rewrite your information. And specifically to get that information back into the format that you needed for your conclusion. So here, state the conclusion. Please note your conclusion is going to be that Q statement from above. So notice here in terms of new work, you'll be given the implication if P then Q. So this first part and this last part you'll have with no work. You're going to have to do the middle 3 statements is what you'll be dealing with in terms of writing up these proofs. Now before we get into an example, let us go ahead and do a little bit of background information. We have, I believe, talked about all of this stuff before, but these are the key mathematical definitions and facts that we're going to need for the examples I've prepped up. Okay. So the first thing that we've got here in our background information is the definition of something called divides. You guys have dealt with this in one of your homework sets. So here's what you got. You got 2 integers. They have to be integers. So A and B are 2 integers. Then we say that A divides B if the following formula is true, if B equals A times K, where K is some other integer. Notice the key things here. The relationship between A and B. The fact that K is an integer and your original 2 numbers are integers. If you want to say something like 1/2 divides 3/7, that doesn't make sense because you didn't start off with integers. Notice what this means in layman's terms. This means that your A is a factor of B. So if A divides B, that means A is a factor of B. Mathematically speaking, this is the same as saying A divides into B evenly. Now, in terms of symbols, this is that vertical line that you guys have seen prior to now. You've got A divides B, or A is a factor of B. And this vertical symbol right here, please note, is not a mathematical symbol like multiplication. It is simply a logical shorthand. So if you write something like A divides B equals AK or something like that, this here is complete nonsense. It has no meaning whatsoever. That's a really common mistake that people will do with divides. Now, next thing that we're going to need for the section is talking about the definition of even and odd. We've talked about both of these 2 definitions in the past. The formal definition of an even number is a number that's divisible by 2. Notice here, if we put this in the symbols of divides, just a second, I need to get rid of that A. This is 2 divides A right there. Okay. In other words, 2 is a factor of A. Now for an odd number, if A is an odd number, the official definition is right here. A equals 2n plus 1. Watch out. Plus and minus 1 are sometimes used interchangeably for the definition of odd. The negative 1 is not the definition of odd. It is simply something else that you can do. Okay? Notice here, another way of phrasing this is 2 is not a factor of your odd number. And the last definition that we're going to need is a definition of a perfect square, and there's more than one way to define a perfect square, so let me show you 2 of the common ones. The first one is, suppose you have some integer n. It's a perfect square exactly when you take the square root of that integer, and the square root is still an integer. Okay? Now, this here is totally accurate, but sometimes it's easier to go the other way. So here, if A is an integer, then A squared is a perfect square. Notice it's the exact same information. It's just phrased a little bit differently, so you don't have the square root symbol involved. So, let us get into an example. So the example that we have here is we would like to prove that the sum of 2 odd numbers is even. So first thing that you want to do is you want to be able to write this in an if-then statement, where the if part of the statement I'm going to go ahead and label as P, the then part of the statement we're going to go ahead and label as Q. So if we're looking at converting this into an if-then statement, the if part needs to be what we start with. So notice what we're starting with here. We want to prove that the sum of 2 odd numbers is even. So we're going to end, our conclusion is going to be the sum is even. But what do we have to start with? We're going to have to start with these 2 odd numbers. Okay? So our if part here is going to be A and B are odd. I went ahead and threw some symbols on because we're actually not going to be able to do this problem or write this proof if we don't have symbols representing our 2 numbers. Then we can actually write out that sum, and that sum right there would be A plus B, and we need it to be even. Now, notice a couple of things. One of the things is we are dealing with if P then Q is the format that we're dealing with this example. We also have, when we picked our 2 symbols for our 2 odd numbers, we on purpose made sure A and B here are 2 different symbols, and that's because there's nothing that says these have to be the same 2 odd numbers. It just says they have to be odd numbers. So we're going to go ahead and use the direct method here. And remember what we're going to do with the direct method. The very first thing that you do is you start off and restate your if part of your if then. In other words, you state the given information. Okay? So when we state this given information, one of the things that we're going to do is we're going to be defining what symbols we use, because in the example, in that statement, that first sentence that was thrown in at the beginning, it didn't give you the labels for your 2 odd numbers. So here we say, hey, suppose A and B are odd numbers. This tells you the symbols that we're going to use for 2 odd numbers. It also tells you your starting point, your if statement P, and remember the if part of an if-then statement is also called your hypothesis. Now, next thing we want to start thinking about is where we're going to end. We're going to end when the sum of A and B is even. But we got to get there. So before we can even get there, we start looking about what we know. So at this point, the only thing we know is we've got 2 numbers. They're called A and B, and they're odd. So the only useful piece of information that we have right now is that our 2 numbers, A and B, are odd. So we're going to pull out the definition of an odd number. So the definition of an odd number says that each of those 2 guys, both A and B, can be written as 2 times some integer plus 1. Now notice I stated here that we were going to be using the definition. So this tells your reader that you're going to be using the definition. Gave the formula of how to rewrite your 2 odd numbers, and made sure to list out these 2 new symbols that we've pulled into play here have to be some integer because that matched our definition of odd. Note also the K and the T are not the same symbol, and they are not the same symbol because A and B don't have to be the same odd number. And if you actually use the same symbol in the location there, the K and the T, you would get the same formula for A, the same formula for B, and that would necessitate that A and B were equal, which is something that's okay to be true, but not something we're requiring. Okay? So now we've exhausted everything that we can possibly do before we got up to looking at the sum of A and B. So let's now go ahead and look at the sum of A and B. So at this point, this is where we're actually going to do applying our algebra, doing a little bit of our logic, and putting everything that we know so far together. Okay? So we're looking at A plus B. Now we just found a formula or a way to rewrite both B as well as A. So I'm going to go ahead and replace the symbol A with what A is supposed to equal, replace the symbol B with what B is supposed to equal. So that's just a direct plug-in. Now, remember what we're trying to get to. We're trying to get to that the sum A plus B is even. Now remember what the sum being even means. We don't care about the sum part, but being even means you have a factor of 2. You're divisible by 2. 2 evenly divides you. Personally, I think it's way easier for people to think about this as 2 is a factor of our sum. Now, when we just had the symbols A plus B, I don't know if 2 is a factor of that. But now that we've rewritten A and B in terms of these K's and T's, this is something that now has got some 2's involved. So we're going to try to see if we can factor a 2 out of that. The first step is go ahead and combine all terms. Then you notice there actually is a 2 in each one of those terms. So we'll factor out our 2. Now, at this point, everybody starts thinking, hey, yes, we're done. But we're not done yet because we actually have to state our conclusion and explain why this gives us the answer that we want it to. So this is where we pull back our definition of even. And even said you had to have 2 times some integer. So let's double check. Is K plus T plus 1 an integer? Well, K and T originally were integers. 1 is definitely an integer. So we add up 3 integers and we're going to turn out to end up having still an integer. So yes, we've got 2 times some integer was our sum, which means we then simply say, yup, we've got our definition of even, so that sum is definitely even just by applying that same definition. Okay. Now, please note, the proof part is this. The writing to the side originally was just us doing a little scratch work of pulling out where we started, where we ended, and what method we were using, just scratch work. This part to the side was just me tagging what we were doing at each line. In terms of the actual proof, it is simply this little teeny tiny paragraph right here, although it looks big because it's filling up the entire slide. And inside of this paragraph, we do have a little bit of algebra manipulation right there in the middle. And that's a proof.